Well, we've come to the end of this subject, and we've already shown you a universal machine, which is down to the level, an evaluator, is down to the level of detail you could imagine you could make one. This is a particular implementation of Lisp built on one of those scheme chips that was talked about yesterday, sitting over here. This is mostly interface to somebody's memory with a little bit of timing and other such stuff. But this fellow actually ran Lisp at a fairly reasonable rate as interpretive. It ran Lisp as fast as a DEC PDP-10 back in 1979. And so it's gotten pretty hardware, pretty concrete. We've also dazzled you a bit with the things you can compute. But is it the case that there are things we can't compute? And so I'd like to end this with showing you some things that you'd like to be able to compute that you can't. The answer is yes, there are things you can't compute. For example, something you'd really like is if you're writing a compiler, you'd like a program that would check that a thing you're going to do will work. Wouldn't that be nice? You'd like something that would catch infinite loops, for example, in programs that were written by users. But in general, you can't write such a program that'll read any program and determine whether or not it's an infinite loop. Let me show you that. It's a little bit of minor mathematics. Let's imagine that we just had a mathematical function before we start, and there is one, called S, which takes a procedure and its argument, A, and what S does is it determines whether or not it's safe to run P on A. And what I mean by that is this. It's true if P applied to A will converge to a value without an error. And it's false if P of A loops forever or makes an error. Okay. Now that's surely a function. There is some, for every procedure and for every argument you could give it, that is either true or false, that it converges without making an error, and you could make a giant table of them. Okay. But the question is, could you write a procedure that computes the values of this function? Well, let's assume that we can. Suppose that we have a procedure called safe that computes the value of S. Okay. Then I'm going to show you by several methods that you can't do this. The easiest one, or the first one, let's define a procedure called diag1. Given that we have safe, we can define diag1. Diag1 to be the procedure of one argument P, which has the following properties. If it's safe to apply P to itself, okay, then I wish to have an infinite loop. Otherwise, I'm going to return 3. Maybe it was 42. What's the answer to the big question? Where, of course, we know what an infinite loop is. An infinite loop to be a procedure of no arguments, which is that nice lambda calculus loop, lambda of x, x of x, applied to lambda of x, x of x. So there's nothing left to the imagination here. Okay? Well, let's see what the story is. I'm supposing it's the case that we worry about the procedure called diag 1 applied to diag 1. Well, what could it possibly be? Well, I don't know. We're going to substitute diag 1 for p in the body here. Well, is it safe to compute diag 1 of diag 1? I don't know. There are two possibilities. If it's safe to compute diag 1 of diag 1, that means it shouldn't loop. Oh, that means I go to here, but then I produce an infinite loop. So it can't be safe. But if it's not safe to compute diag 1 of diag 1, then the answer to this is 3, but that's diag 1 of diag 1, so it had to be safe. So therefore, by contradiction, you cannot produce safe. For those of you who were boggled by that one, I'm going to say it again a different way. Just one more alternative. Let's define diag 2. These named diag because of Cantor's diagonal argument. These are instances of a famous argument which was originally used by Cantor in the late part of the last century to prove that the real numbers were not countable, that there are too many real numbers to be counted by integers, that there are more points on a line, for example, than there are counting numbers. It may or may not be obvious, and I don't want to get into that now. Okay. But diag 2 is, again, a procedure of one argument p. And it's almost the same as the previous one, which is if it's safe to compute p on p, then I'm going to produce, if, then I want to compute some other thing other than p of p. Otherwise, I'm going to put out false. Where other than, it says, whatever p of p is, I'm going to put out something else. I can give you an example of a definition of other than, which I think works. Let's see. Yes, where other than be a procedure of one argument x, which says if it's eq x to say quote a, then the answer is quote b. Otherwise, it's quote a. That always produces something which is not what its argument is. That's all it is. That's all I wanted. Well, now let's consider this one, diag 2 of diag 2. Well, look, this only does something dangerous, like calling p of p, if it's safe to do so. So if safe is defined at all, if you can define such a procedure safe, then this procedure is always defined and therefore safe on any inputs. Okay? So diag 2 of diag 2 must reduce to other than diag 2 of diag 2. And that doesn't make sense. So we have a contradiction, and therefore we can't define safe. I just wanted to do that twice, slightly differently, so you wouldn't feel that the first one was a trick. Okay? They may be both tricks, but they're at least slightly different. So I suppose that pretty much wraps it up. I've just proved what we call the halting theorem. Okay? And I suppose with that we're going to halt. I hope you have a good time. Are there any questions? Yes?
What is the value of s of diag 1?
Of what?
S of diag 1. If you said s is a function and we can indeed
I don't
tabulate all
know.
the values.
I don't know. It's a function, but I don't know how to compute it. I can't do it. I'm just a machine too. right? And there's no machine that, in principle, it might be that in that particular case you just asked, with some thinking I could figure it out. But in general, I can't compute the value of S any better than any other machine can. There is such a function. It's just that no machine can be built to compute it. Now, there's a way of saying that should not be surprising. Going through this, I don't have time to do this here, but the number of functions is very large. Okay? If there's a certain number of answers possible and a certain number of inputs possible, then it's the number of answers raised to the number of inputs is the number of possible functions, okay, on one variable. Now that's always bigger than the thing you're raising to, than the exponent. The number of functions is larger than the number of programs that one can write by an infinity counting argument. So there must be, and it's much larger. So there must be a lot of functions that can't be computed by programs. Yeah.
A few moments ago, you were talking about specifications and automatic generation and solution. Do you see any steps between specifications and solution?
Steps between? You mean you're saying how you go about constructing devices given that you have a specification for the device?
There's a lot
Sure.
of software engineering that goes from specifications through many layers of design and then implementation.
Yes.
I was curious if you think that's realistic.
Well, I think that some of it's realistic and some of it isn't. I mean, surely if I want to build an electrical filter, okay, and I have a rather interesting possibility, right? Supposing I want to build a thing that matches some power output tube of a radio transmitter, right, to some antenna. Okay, and I really have this output tube out here. And the problem is that they have different impedances. I want them to match the impedances. I also want to make a filter in there which is going to get rid of some harmonic radiation. Well, one old-fashioned technique for doing this is called image impedances or something like that. And what you do is you say you have a basic module called an L section. Looks like this. Okay, and this, if I happen to connect this to some resistance R, and if I make this impedance X, XL, and if it happens to be Q times R, then this produces a low-pass filter with a Q square plus 1 impedance match. Okay, just what I need, because now I can take two of these, hook them together, like this. Okay. Okay, and I take another one. Okay. And then I'll hook them together like that. And I have two L sections hooked together, and this will step the impedance down to one that I know, and this will step it up to one I know. Each of these is a low-pass filter getting rid of some harmonics. It's a good filter. Okay? It's called a pi-section filter. Great. Okay? Except for the fact that in doing what I just did, I've made a terrible inefficiency in this system. I've made two coils where I should have made one. Okay? And the problem with most software engineering art is that there's no mechanism other than peephole optimization and compilers for getting rid of the redundant parts that are constructed when doing top-down design. Okay? And it's even worse. There are lots of very important structures that you can't construct at all this way. So I think that the standard top-down design is a rather shallow business. It doesn't really capture what people want to do in design. I'll give you another electrical example. Electrical examples are so much clearer than computational examples because computational examples require a certain degree of complexity to explain them. But one of my favorite examples in the electrical world is how would I ever come up with the output stage of this interstage connection in an IF amplifier. Got some little transistor here, and let's see. Well, I'm going to have a tank, and I'm going to hook this up to, say, I'm going to link couple that to the input of the next stage. Okay? Here's a perfectly plausible plan. Well, except for the fact that since I put that going up, I should make that going that way. Okay? Here's a perfectly plausible plan for a... no, I shouldn't. I'm dumb. Excuse me. Doesn't matter. The point is, here's a perfectly plausible plan for coupling two stages together. Okay? Now, what the problem is what's this hierarchically? It's not one thing. And hierarchically, it doesn't make any sense at all. It's the inductance of a tuned circuit. It's the primary of a transformer. And it's also the DC path by which bias conditions get to the collector of that transistor. And there's no simple top-down design that's going to produce a structure like that with so many overlapping uses for a particular thing. Playing Scrabble, where you have to do triple word scores or whatever, is not so easy in top-down design strategy. Yet most of real engineering is based on getting the most oomph per effort, and that's what you're seeing here. Yeah.
Is this the last question?
Apparently so. Thank you.